Hello everybody, this is Professor Iris Miano, Math 2, Day 9 lecture covering sections 3.2, A11, which is an appendix section, and also a little bit of 2.7. Very ambitious amount of information we're going to cover today, so this lecture video is going to be on the long side, which I'm sure you're already able to see before you even pressed play. So, the main thing we'll be focusing on in this lecture is to find the real zeros of a polynomial function, as is the title of this section. We're going to be revisiting elements of polynomial long division, mostly in the form of synthetic division. Actually, we're not going to do any polynomial long division in this section. We're going to rely on finding the remainder by simply plugging in suspected zeros and also performing synthetic division on binomial factors that allude to potential zeros in order to test to see if they're actual zeros by virtue of looking at the remainder, which is going to be the last calculation in the process of synthetic division. That'll allow us to create depressed functions in order to eventually factor larger degree polynomial functions. So lots of fun ahead in that respect. So we want to just revisit what it means to divide polynomials. So when you do so, just like when you divide real numbers, you get a quotient. And if there's a remainder, you can add it to the quotient in the form of the ratio of the remainder over the divisor. So all of those elements are listed here as well. And this other bit in which the components are labeled in blue, this is called the related multiplication of a division problem, which is this first little bit off to the left here. Okay, so that's all more or less review. What we want to be focusing on is having some semblance of when x minus c, so a very simple binomial factor, is indeed a factor of a polynomial function f of x. So we can do this by plugging in the c value of the potential binomial factor. And so let's go ahead and do that for this first example. And if we get a zero factor, a zero output from this f of c value. This is something we're going to get into in a little bit of a subsequent example. Then we can say that that c factor is a zero. But I guess I'm getting a little bit ahead of myself. Let's just do what this first example states, which is to find the remainder if f of x presented here is divided by x minus 4 to start with part A. So the first thing that we'll want to do is recognize that in this format here with this theorem, x minus 4 has a c value of, hold on, let me draw. C value is 4 in this case. So really we're saying what's the value of f of 4? So plugging it in, it'll look like this. 6 times 4 to the third power minus 6 times 4 to the second power. My goodness, so this will be a lot of work to simplify, particularly if you're doing it by hand. Even if you're doing some button pushing, it's a bit of typing. So let's just assume that we did the button pushing, and what would we get? If you simplified all of this out, you would get 108. So therefore, this is the remainder, according to this theorem right here, remainder. Okay? Now, what if we put in, instead of 4, investigating if x minus 4 was a factor, let's see if x plus 2 is a factor. So in this case, the c value that we want to plug into our f would be -2. So note how the signage needs to be addressed appropriately. So what's f of -2 look like? Well, when we just plug it in, it looks like this. So give me a moment to write it all down. Oh, so boring, I know. A little tedious, this bit. But if we simplified it all the way down, you would get ... that it equals 0. Okay, so that's the remainder. And what we can glean from a zero remainder is that this c value is a 0 for the function, and x plus 2 is a factor for it. So if you factored this all the way down, which is something that we're going to do for similar functions later on in the lecture, you would know that this is a 0 and that's a factor. Okay, moving on. Yes, so one of these yielded a 0 remainder tells us that the corresponding divisor is indeed a factor, and then the other one is not. The 108 remainder, that corresponding binomial bit was not a factor. Okay, cool. And so we have the factor theorem that allows us to make this connection here, which is to say, if you have an x minus c factor that you are confirming is a factor of your original f of x function, then that means that if you plug in the c value into your function, it equals 0. Okay, and these are interchangeable. That's why they use this phrasing if and only if, which is a code for the biconditional concept, which is to say you could rewrite this statement right here. Excuse me. As two conditional statements, so you could go in the forward direction or you can go in the reverse direction as far as the order of these elements are concerned. It's true either way. Okay, so let's go ahead and instead of plugging in the factor of c into our function, let's practice a little synthetic division in order to determine what the remainder is when your c value is, in this first case for part A, a 2. Okay, so again, we could go the f of 2 route and figure out what that is, or use synthetic division. Which I think is just a little bit more fun. So let's go ahead and do that. And here's the setup. So if you've ever seen synthetic division before, you know what's up. If you haven't, I'm delighted to demonstrate this for you. So yes, obviously your c value here is 2. The 2 goes outside of the house in this synthetic division setup, and along this row, in line with the 2, you need to put the coefficient and constant term of all of the terms that occur in your function, plus zeros for any to be placeholders for any missing terms. And by that I mean there's no third degree term here, and there's also no first degree term, so those need 0 placeholders. So the numbers in this top row will therefore be 4, 0, -15, 0, and -4. All right, yes, I have that down correctly. The first thing that you'll do in this process is drop down the first number in the house and have it kind of just plop right outside the house, okay? Then you're going to multiply through the c value out in front with the 4 that got dropped down, or whatever number comes down here, and put the remaining product in this position directly under your 0, so that'll be an 8. Then you add the 0 to the 8 and you get 8. Multiply through again the 2 with the 8, and you're going to get 16 in this position. -15 plus 16 gives you a 1. Multiply through again, and you're going to get a 2 in this position. 0 plus 2 is 2. Multiply through one last time, and you're going to get 2 times 2 equals 4. Ooh, and then something magical is happening here. These 4s are going to cancel out, and you're going to get a 0. So a 0 in this position, it's the remainder. If you had done polynomial long division on an x minus 2 into this function right here, you would get, these numbers give you the quotient right here. It would be 4x to the 4th plus 8x squared plus x plus 2, 0 remainder, okay? So anyway, so I'm giving you way more information that you need for this problem. What we want to glean from this is simply that this 0 remainder means that x minus 2 is a factor of f of x. Great. Let's see if this next binomial, x plus 1, let's see if it's a factor of f of x. So here your c value is -1. You're going to put that outside the house. And you're going to line up all of those same coefficients, 0, 4, negative 15, 0, and negative 4. You're going to take that first one and drop it, multiply through, negative 1, your C value, and your 4, and you're going to get negative 4. This first position, go ahead and add, and you will get negative 4. Multiply through, and you'll get negative 1 times negative 4 is positive 4. Add negative 15 to it, and you're going to get negative 11. Multiply through that negative 1 on the negative 11, and you'll get positive 11. Plus the 0 gives you 11. Multiply one last time, and then we'll be done with this process. Negative 1 times 11 gives us negative 11 once again. Add that to the negative 4, and you get negative 15. So this is still your remainder, but it's not 0 this time. Okay, and this would be the number that would pop out if you plugged in a negative 1 into the function. It's the same thing, same result, same end result, but different process, of course. So you pick which one you like better. I like this synthetic division because it just gives me more information, and it's something along the lines of what we're going to need to do for further down the road processes in which we're going to actually have to factor all of these polynomial functions with higher degrees. So synthetic division is kind of the way to go for that, in my opinion. So this remainder not being non-zero, this means that x plus 1 is not a factor of f of x. Cool, cool. Moving on. We've got lots to cover, so I'm just going to go straight to the next thing without a lot of preamble in between. Okay, so notice that we have some information, gleaned from these this particular function. We were able to determine that one of the binomials was a factor and the other one wasn't. But wouldn't it be nice to know how many zeros we should expect, at least at maximum? And wouldn't it be nice to know what the signs of those zeros might be? Well, here is a theorem, the number of real zeros theorem, that alludes to the connection between the degree and the number of possible real zeros, and it's basically the same thing. So you can't have any more real zeros than the degree. You can certainly have fewer than the degree states, but the maximum possible would be the degree. Okay, so basically it's the degree equals max number of real zeros. Okay. If you are interested in doing a little preliminary stuff before you try and find out what the actual values of your zeros are, if you just want to know how many of each sign you have, how many are positive and how many are negative, you can bust out Descartes' rule of signs. Okay, so for the first start of the process, you just look at the original function and you look for what's known as variations in the sign. So as you move from one term to the next, from left to right, if the sign changes, then that's going to be a variation of sign. So I'm going to highlight that here. Variations in the sign. If you see that with the original function, that tells you however many variations of sign you see moving from one term to the next, from left to right, that tells you the number of positive real zeros. And if you plug in a negative x into your function, the signs from one term to the next may or may not change when you do that, but you count the number of changes that you see, and that's again your number of variations in sign. That's going to determine how many negative real zeros you have. So let's go ahead and bust out this fun little game here on a new function. First, tell how many real zeros can we expect? Well, what's the degree of this function? It's degree 4. So degree equals 4. So 4 is the maximum number of real zeros we can expect? Okay, now how many of them are positive zeros and how many of them are negative zeros? Let's take a look. So look at the original function. I'm going to go ahead and rewrite it here just so we can do this little variation in sign analysis. Okay, so here we go. Notice that the first term here is positive, right? There's no negative sign out in front. So we're going from positive, and if we say hello to the neighbor there, are we changing the sign? Well, no, because that next, that second term is being added, so it's the same. But as we go from the second term to the third term, oh, did we change the sign? Yes, we did. So we have a change. Note that. And then from this negative term, we're going to go to the constant term, which is also negative, so it's the same once again. No change in that last movement. Okay, so we had one change. Oh, I wanted to do this other kind of a color there. So this means that we can expect one positive real zero. Okay, now similar thing, but let's look at f of negative x. Well, that'll be 5 times negative x to the 4th power plus 2 times, it's supposed to be a plus, negative x squared minus 6 times negative x minus 5. Okay, so upon simplifying it, oops, hold on, there we go. The first two terms are not going to change, right, because of the evenness, you know, of those first two terms. So that'll be 5x to the 4th plus 2x squared. But this third term is going to change its sign. It's going to turn into plus 6x and then minus 5. So again, because this first term is positive, going from here to here, it's the same sign, same again. Different. We had a change in the signage. There's a variation in sign from here to here, from the first degree term to the constant term. So we have one change. So that means we can expect one negative real zero. But how many real zeros could we have possible? Well, we could have 4 at most, but only one of them is positive and only one of them is negative among the real zeros. There's 2 zeros left, so that means, and we're going to get it deeper into this a little bit later, those last 2 zeros are going to be complex conjugates. Again, that's a discussion for another time. All right, now that tells us how many zeros we can expect at most, what number of them are positive and negative. Let's get a little deeper into this analysis with the zeros, or rational zeros theorem, which will tell us what all of the possible values are for our zeros. Now, it's not going to tell you exactly which one of them are zeros, but it's like among all of these possibilities, you will find your zeros in the list that we're about to create here using this theorem. So notice that we have a generic function broken down into its individual terms in standard form, where we have, you know, the leading term here, and it goes in descending order of degree all the way down to the constant term. And neither the leading coefficient nor the constant term can be 0. So if we can come up with this list of ratios, P over Q. Now, P is a factor of the constant term, and Q is a factor of the leading coefficient, okay? So we need to list all of the possibilities here and list all the possibilities of that particular ratio, P over Q. Let's go ahead and tackle this with example 4. We're going to list the potential zeros of f of x equals 6x to the 4th minus x squared plus 2. Okay, so here, let me get my notes ready. And here we go. So the first thing we want to notice is now we have 3 terms here, right? So whatever, a to the n sub n, that's going to be your leading coefficient, that's going to be 6, and your a sub naught is going to be 2, right? So your A sub n is actually associated, if you look back up here, is a factor of your Q, which is the denominator. So I always put P list and Q list kind of like this. And then I point to them, and they're kind of switched, like the way that you think about them, or the way that I think about them is switched a little bit. So I always do a little bit of an arrow pointing here just to keep it straight which one I'm talking about, okay? So let's go ahead and list all of the factors that are possible for P and Q. So P being all of the factors of 2. And not that we did the sign analysis earlier, the Descartes rule of signs, but let's just say that we did, and we had at least some positive or negative zeros, okay? Let's just assume that here without taking the time to actually do it. Okay, so then we would need to list all of the possible values, factors of 2. So you can go positive or negative 1 or positive and negative 2. Again, accounting for the possibility that there are negative zeros and positive zeros. Let's just assume that that's the case. And then down here for Q, you need to list all possible factors of 6. So you'll start with plus or minus 1, plus or minus 2. In addition to that, another factor is plus or minus 3. And of course, the number itself, plus or minus 6. Okay, so now we need to list all possible ratios of P over Q. P over Q, therefore, could be, and there's a systematic way that I like to do this. So there's the numerator values, right, of P. There's only 2 of them. So you'll have your first one be fixed on the denominator, right, of 1. And then you'll go through both of the possible P values. So there's 1 for P or 2 for P. So this is just fixing the first Q value in the denominator, go through both of the options for P. And you can reverse it if you have more P factors versus Q factors. It's just whatever's going to work for you. So then plus or minus, let's go for the next 2. Again, go 1 and 2 for the numerator, and then fix the denominator at 2. Okay, and then systematically go for the next 2 ratios, which will look like what? Fix the denominator at 3, and then go 1 and 2, right? And then lastly, we'll fix the denominator at we need a plus or minuses, fix it at 6, and then do your 1 and 2 in the numerator. So that exhausts all of the different possibilities, but you may notice that some of these values have repeated, right? So it might be a good idea to say what they simplify to, and we'll see if there's any repeats. So this one simplifies to 1, this one simplifies to 2, this one simplifies to 1/2, this one simplifies to 1, so it's a repeat, so we can actually leave it out. This one's a 1/3, 2/3, 1/6, and that one is another 1/3, because that's what it simplifies to. So go ahead and eliminate these 2, and that'll allow us to list the entirety of the list of possible factors, which is your P over Q. So let me rewrite that here, cleaning house a little bit. P over Q, therefore, which is the list of potential zeros, is 1 plus or minus 1, plus or minus 2, plus or minus 1/2, plus or minus 1/3, plus or minus 2/3, and plus or minus 1/6. Okay, and these are all supposed to be pluses and minuses. They got a little sloppy there, but I think they look okay to me. All right, and that is your exhaustive list. Now, not all of these are zeros, but any one of them could be a 0, okay? Cool. So let's put all this information together and actually find all of the zeros for a polynomial function, okay? Not only are we going to find all the zeros, but we're going to rewrite the polynomial function in factored form as well. And I have lifted the summary of steps that are good for us to go through in order to streamline this process. So here we go. Our function is as follows. We're going to use the degree of the polynomial to determine the maximum numbers of zeros. That's step one. So step one, let's actually go back to this magenta color. The max number of real zeros, is the degree. What's the degree? It's 3, okay? So check that off your list. Step two, we are going to do the Descartes rule of signs. So look at the original function, and from here to here, right, it's the same. Ooh, yeah, we have a variation in sign there. So that means that we have one positive real zero. So that's a change. So one positive real zero. I'm going to actually need to plug in f of negative x for this next bit. So that'll be negative x to the third power plus 8 times negative x squared plus 11 times negative x minus 20. Simplifying it down, we'll get negative x cubed plus 8x minus 11x minus 20. So, and I'll do a different color for variations. We have a change here, a change there, another change. And then same for this last step. So that means that there are 2 negative real zeros. Put that right underneath here. Okay, rule of signs, check. Step 3, this is overwhelmingly the most intense step, but we have all of the elements now in order to perform it. We just need to, what do we need to do? If the polynomial has integer coefficients, which it sure does, we use the rational zeros theorem to identify those rational numbers as potentially, which potentially could be zeros. Now, looking at back at step 2, we have positive and negative real zeros, so we're going to have to entertain the positive and negative versions of all possible factors for the leading coefficient and also the constant term for p and q irrespectively. All right, so let's go ahead and put a sub n down. The leading term, or the leading coefficient rather, is 1, and a sub naught is negative 20, right? So what are all the possible factors there? So if we put p and q like this, remember, do a little kind of a switcheroo. And so the possible factors of q, let's do that one first, or that's the easy one, it's plus or minus 1, and that's it, real short list. Now for p, it'll be plus or minus 1. Everybody's got that one. Or, you know, if we knew at step 2 that they were all, the zeros were positive or all those zeros were negative, we would just take one of these signs here. But we need to have both because we have both kinds of zeros there. All right, so there's also factors of plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 20, or 10, excuse me. 10's in the mix, yep. And then plus or minus 20. Now that's the exhaustive list of all possible factors that could be included for p. So that means that the, believe it or not, the p over q list is the same as just the p list, because the denominator for each of those is just going to be a plus or minus 1. So it's going to be redundant. So I'm just going to say off to the side here, p over q is actually just equal to p as far as the list of all possible values. So when you have so many options here, the general rule of thumb is to start with 1. Start with 1 as your c value in the process of the synthetic division that you're going to use in order to see if x minus 1 is a factor of f of x, okay? So let's see equal 1. So then 1 is outside the house, and we're going to list all of the coefficients. And what were they again? They are 1, 8, 11, and negative 20. Okay, and let's go through the process. The first thing you do is drop down that 1, and then you're going to multiply through the 1 to the 1, and it's going to become a 1 right here. 8 plus 1 is going to give you 9. Multiply through. Again, and you get 9 in this position. 9 plus 11 is 20. Ooh, you guys see what's going to happen here? Oh, that was lucky. Yeah, you might not get it the first time, but we did, because check this out. We have a 0 remainder. 0 remainder. Very exciting. So that means that x minus 1 is a factor. And furthermore, because of the nature of the synthetic division, we are given the depressed function, which is take the coefficients and create another polynomial 1 degree less than the original one, and it'll give you x squared plus a 9x plus 20. And it has a particular name. We call it Q, or sorry, that's a G. Q1 of x, which is designated as the first depressed equation. So I'll label it first depressed equation. And by depressed equation, we mean the resulting equation that you get from the synthetic division. It's a depressed equation, is the remaining bit from the non-zero bits that you get to glean. And it's only because we have a 0 remainder that we take this and we're going to use it, and we actually care about it. It's actually the remaining part after you took out a factor of x minus 1. Okay, so now we want to look at this quadratic function that's left and say to ourselves, can we factor it? I mean, we could always do the synthetic division over again with any number of, the other factors that are there. Or we could just say, if we recognize it's factorable, then let's just factor it. So I recognize that this is factorable, and it is factorable as x plus 4, x minus 4. So q sub 1 of x, or sorry, x plus 4x plus 5 is what I meant to say. So therefore, the zeros are 1 from this synthetic division endeavor, -4 for this little bit right here, and also -5. We'll go ahead and circle that. And then we also want to rewrite the f of x in factored form. So f of x is, well, there was the factor of x minus 1 that we were able to investigate with the synthetic division, and then I factored the rest for x plus 4, x plus 5. So there is your factored form. Fun, right? Now that one was relatively simple. We've got another one on deck here that we want to do in example 6. Let's see another one, okay? And yes, we have a 4th degree polynomial. It's going to be a little bit more challenging. Very exciting though. We can get through it. Don't you worry. Here we go. First step, what's the maximum number of zeros that we can have? Well, that would be 4 because that's the degree. So max number of zeros is 4. Step 2. Descartes' rule of signs. So here we'll look for variations in sign. Look, same, 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 same. No changes. Same Z's all around. Okay, so that means that there are no positive zeros. No positive real zeros. I guess we should specify. I know what you're thinking. Well, then all the rest of them are negative zeros. Hold on. That might not necessarily be the case. They might all be complex, in which case they wouldn't be categorized as positive or negative. And by complex, I mean not real complex zeros. Okay, so let's go ahead and do the other end of it and go f of negative x and see what we get. So that'll be 3 times negative x to the 4th power plus 4 times negative x to the 3rd power plus 7 times negative x to the 2nd power plus 8 times negative x plus 2. Okay, and that simplifies to 3x to the 4th. No change in that one, but this one changes, right? Minus 4x to the 3rd plus 7x squared minus 8x plus 2. And as you can see, we're going to have lots of changes here because from positive or negative, that's a change. From negative to positive, that's another change. Oh, another change again. And I'm just doing C for change, I guess. You know, I had been writing out the whole thing, but, you know, I'm getting lazy now and I just want to go through this as quickly as we can, but also accurately. All right, so it looks like it was changes every single time we went from one term to another. So that's 4 changes altogether. So that means there are 4 negative real zeros. So knowing that there are no positive real zeros, that's going to help us narrow down the list of possible, possible zeros in the next step, okay? So because we have integer coefficients, we can use the rational zeros theorem. Note that a sub n is 3, and that a sub naught, or sub 0 rather, is 2. So our P and our Q are going to be as follows. And also because we had just done this thing where they were all, okay, so the factors themselves, sorry, I'm just looking at my notes here, are indeed plus or minus 1, plus or minus 2, and plus or minus 1, plus or minus 3, and that's what you should expect because both of these numbers are prime. And now I need to have plus or minus for the lists of P's and Q's, but then when I come to the ratio, only the negative ratios are going to be in play here. So this P over Q, therefore, the exhaustive list will therefore be, and I'm just going to go straight to it and not do the in-between stuff, will be negative 1, negative 2, negative 1/3, negative 2/3. Okay. Great. So let's start with the, because we don't have a positive one as a possible 0, let's start with the other easiest to work with one, which would be negative 1. So let's let C equal negative 1. So we'll put negative 1 outside the house, and we'll list all of the coefficients, which are what? 3, 4, 7, 8, 2. In that order. Okay, let's start the process. Drop that 3 down first. And we'll multiply through. Oops. Like so. We'll get a negative 3 right here. 4 plus negative 3 is going to give us a positive 1. Multiply through with the negative 1. We'll get negative 1 here. Add and we'll get a 6, if I'm not mistaken. Oh, let's maintain our color scheme though. Multiply through and we'll get negative 6 in this position. Negative 6 and 8 added together give us a 2. Oh, you can see where this is going, huh? That's lucky yet again. I mean, I chose this on purpose, so I wouldn't waste time presenting this to you. but that'll give us a -2, and that gives us a 0 remainder. Now, just to be clear, if you go through this process with the C that you pick as a possible 0 and you get anything other than 0 here, you have to start the synthetic division process again with another potential 0. So since I happen to have it here, I can just look at the depressed function, which is, so I'll go ahead and point to here and say q sub 1 of x is therefore 3x cubed plus x squared plus 6x plus 2. Okay, and yeah, x plus 1 is a factor, so I could just kind of like, you know, put that in the side burner for the moment. So the thing that I'm left with here in this q sub 1 of x, the first depressed what's it called, the first depressed function in this synthetic division process, I noticed that it's 4 terms long, and it looks like it's a good candidate for factoring by grouping. So what does that process look like? Well, you want to group your factors by 2's. If you can maintain the original groupings, like or the most generic the obvious groupings, the ones that are just there, then all the better. And you want to factor out the GCF of each grouping. So here, the GCF of this first box is going to be x squared, right? So we'll have x squared taken out, and the remaining bits will be x plus, or 3x plus 1, right? And then the GCF of the second grouping will be a 2. You want to keep this plus sign there. And we'll be left with 3x plus 1. So luckily, these binomial factors match. So therefore, the common factor of 3x plus 1 can be pulled out to the front. It's supposed to be a plus 1. And then the remaining bit will be x squared plus 2. Now, x squared plus 2 is not factorable, okay? So we're going to find in further analyses later on that this will yield non-real complex zeros. So that's just a discussion for another time. So in any event, we cannot factor this any further, and we can put this together with the factor of x plus 1 that we deemed an actual factor of f of x in order to do this. So the real zeros, that are possible here are real zeros, I guess I'll specify, -1, and also -1/3 is what you're going to glean from this. That's when this binomial factor is equal to 0. Okay, and that's it. You may know, and I kind of, spoiled it and said, oh, this is going to yield some complex zeros. We'll get into that a little bit later. We just want to be concerned with the real zeros, and the factored form of this function, I'll write it over here, is now f of x equals x plus 1. That's dealing with this first part here, and then this remaining factored bit, 3x plus 1, and then x squared plus 2. And that's done. Okay, phew. Let's go ahead and box up that factored form as well. Beautiful. Okay, so notice how we had an irreducible quadratic factor, right? This guy right here. So there's a theorem that talks about the possibility of that, and it states every polynomial function with real coefficients can be uniquely factored into a product of linear factors and or irreducible quadratic factors. Okay, so we saw a case in point of that. So like I said, these irreducible quadratic factors make for complex zeros, non-real complex zeros, that is. So we're going to explore that more in 3.3. So another thing that we can glean from this is that if you have a polynomial function with an odd degree, then you know at least one of these zeros has to be real, because complex non-real zeros come in conjugate pairs, and by pairs I mean 2 at a time. So if you have, like, let's say a 5th degree polynomial, and the majority of them, like all of them that were possible were complex ones, were complex, then that means at most 4 of them could be complex, 2 conjugate pairs, and then the 5th one, the odd man out, would have to be real. There's just no other way about it. All right, so when your list of potential zeros can be quite long, or if you just want to know what the bounds of the zeros are, you can go to this yellow box right here, which describes the process in which you would find the lower and upper bound, irrespectively, by those bullet points, of a particular function f. So it is a step-by-step process that I'm going to outline here in example 7. So it'll help us streamline the process of finding the zeros. Especially, it's particularly useful if your list of potential zeros is quite long and you want to just trim the fat a little bit. Okay, so let's go ahead and find the bounds, the upper bound and the lower bound. So the way that we find it is we need to go through the first couple of steps like we normally would do. Find the maximum number of zeros. Well, we don't actually need that, but we need to list all the potential. We need to get to the list for sure. And then we can narrow down the list a little bit. Okay, so I'll just go through the motions of the usual thing. Step 1 is usually the max number real zeros. Is 5. And how many are positive and how many are negative? Well, I'm going to give you the result of that Descartes positive and negative process there. So there's 1 positive zero, and 4 negative zeros. Step 3 is we're going to come up with the list. So a sub n, as you can see, is 4. A sub 0 is -2. So we have a smattering of positive and negative, so we have to entertain both. Let's do our P's and Q's list. So the potential factors of P are plus or minus 1, plus or minus 2. Q is plus or minus 1, plus or minus 2, and plus or minus 4. Okay, so therefore your P over Q list is going to be plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 1 over 4, almost there, plus or minus 2 over 4. Okay, and then simplify this all the way down. We get the actual P over Q simplified list as being plus or minus 1, plus or minus 2, plus or minus 1/2, and plus or minus 1/4. Now I know it looks like it's just 4, but there's actually 8 factors here. It's kind of a lot. So in order to do an upper and a lower bound on this, you're going to start with the smallest positive integer among your possible zeros. So smallest, and this is the upper bound process here. Smallest positive integer, which is 1, and you're going to do the synthetic division on that, okay? And if the third row of the synthetic division doesn't have any, all of the signs on all of the numbers in the third row are positive, then that means that this number that you've put in, 1 in your synthetic division, is the upper bound. So let's go ahead and check. 4, 1, 1, 1, -2, and -2. Okay, drop it down. That'll be a 4 here. Multiply through. You'll get 4. It's 5. Multiply through there. You'll get a 5 there. It becomes a 6 now. Multiply through. 6 plus 1 is 7. All right, now the 7 and -2 is a 5. Multiply one last time. And you get a 5 here, and that'll be a +3. So notice that all the numbers here are positive. All positive. So 1 is the upper bound. Okay, cool. Now the process for the lower bound is as follows. Lower bound. You're going to start with your largest negative integer. Largest negative. So the one that's, you know, the largest integer, it has to be an integer, and the one that's closest to 0, that means it's the largest, that'll be -1, okay, out of the list. So now do the synthetic division with -1. And if you have alternating signs in the the third row here, then that means that -1 will be our lower bound. So 4, 1, 1, 1, -2, -2. Okay, first one, drop it down. 4, multiply through. -4. And that'll be a -3 here. It's looking good so far. Let's continue though. It'll give us a 4 a 3 in this position. That'll give us a 4 result. Multiply through. And that'll give us a -4, an output of -3. -1 times -3 is a 3. And the resulting sum here will be a +1. And it's a -1 right here for a -3. Okay. Now, notice that we're not looking necessarily for zeros here. We're just looking to see if in this process for the lower bound, if we have alternating sign. Notice that it's positive here, then negative, positive, then negative, then positive, then negative. If you have alternating signs all the way across, then that means that this must be a lower bound. So let me put a note here. Since signs alternate, -1 is the lower bound. So just as a recap, the upper bound is at 1, lower bound is at -1. Box that up. Whew, okay. There's one last big thing that we're going to talk about here in 3.2, and it's the intermediate value theorem. Now, I call it kind of a forehead slapper of a theorem because it basically says that, okay, if you if you have these two input values of a and b, and a is less than b, and then if you go ahead and calculate the outputs at those 2 points a and b, and the signs change, like if it started off negative and then and by started off I mean if f of a is negative and then f of b is positive, or vice versa, then that means you must have a 0 somewhere in between there, somewhere in the intermediate area between a and b. There must be a 0. Duh, right? If you go from negative to positive in the vertical sense, then you've crossed the x-axis and therefore you have a 0. So that's what this intermediate value theorem is saying. We've probably been taking it for granted, but I just wanted to make sure we all knew and understood it, because that's kind of like the crux of what's being stated here in this entire section. Okay, so one thing we can do for fun, it's actually a little bit tedious, but it's something that we're going to need to practice, is we can go about this process of using the intermediate value theorem to approximate real zeros, particularly decimal, non-integer real zeros, of a polynomial function. Okay, so the first thing you need to know in order to go through this process is that there is a zero on the interval that you choose. And generally the interval that you choose is some unit length interval. Okay, so it's got some lower bound, and then the upper bound is 1 unit away from it. Okay, so if you know that there's a zero between them, and you want to approximate the value of that zero, you can go through this process here, these 4 steps. Okay, so let's go ahead, and I want to outline these 4 steps for you with this particular function, f of x, and we're going to have our approximation correct to 2 decimal places. Okay, great. So the first step that you're going to take in this process is find the output values for inputs that are incremented by tenths to start out with. So by that I mean, okay, we need to find f at 0.1 because that is 1/10 away from the lower bound on this interval, right? Okay, so I already did the work there. You plug in 0.1 into this function, you're going to get negative 0.5192 something 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 something. Right? We don't really need to know too much about the value of this, just that it's starting off negative. So at the moment, it looks like we're below the x-axis, right? Now let's go ahead and find the output value for the next tenth after that, 0.2, and that'll be at negative 0.0672, okay? Dot, 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 something, something. Now, look at this. It's still negative, but it's getting closer to 0, so we're getting pretty close here. Let's take a look at what 0.3's output is for the function, and that'll give us, check this out, y'all, 0.3848, dot, dot, dot. It is positive, so we went from negative to positive. So that tells us that the zero has to be somewhere between 0.2 and 0.3. Cool. So stop, right? Do not calculate the function's value at 0.4. There's no need. You found the place in between using that intermediate value theorem in which the zero has to be within this interval. So now let's take it to a second decimal place. So now it's got to be somewhere beyond 0.2. So go ahead and investigate 0.21 to begin with, the function's value. I already did the work for you. The output here is negative 0.0226. Okay, so we're starting off negative. We're below the x-axis. But what about the next hundredth after that? 0.22. The output there is 0.0219. All right, so we went from negative to positive. So that means that we're somewhere between 0.21 and 0.22. So it's good enough for our purposes to just take the, the lower bound of this tiny interval and say, all right, so correct to 2 places. The zero is 0.21. Okay, and we're done on that one. Whew. So that is finally a wrap on section 3.2 on real zeros of the polynomial function. So we have a little bit more to cover, so stay with me. If you want to take a little bit of a pause break and come back to it, that's perfectly fine. This next 2 sections are going to be more or less review, focusing on complex numbers and complex, how to find complex zeros. We'll talk more or less about what they mean for us in terms of polynomial functions and when they occur in 3.3 next lecture. Okay, so complex numbers. The complex numbers are basically all of the numbers that you can think of that are of the form a plus bi, and that includes all real numbers as well. Real numbers are complex numbers, okay? They just have a 0 imaginary part, so their b value is a 0. It's kind of a mind-blowing thing to think about it this way, but off to the side I can draw you a little bit of a diagram for this. So if you have all of your real numbers here are your real numbers. here are your strictly imaginary numbers. Notice how they're disjoint sets. If you take them all together, right, they make up the complex numbers. The imaginary numbers are still of the form a plus bi, it's just that their a part is 0. And the real numbers are of the form a plus bi, but their b part is 0. Okay, so this is like bi's live in here, your a's live in here, and then everything, the complex numbers are your, if there's room, a plus bi. Okay, cool. All right, so just so that we're clear on that, I is defined as the square root of -1. And it's so funny to me how mathematicians, math instructors, and textbook authors in particular are really just think that the sight of this must be so gross, because I did not even find it explicitly, except for in one little tiny spot in the textbook. Like, it wasn't initially defined this way. Their initial definition of the imaginary unit is only as I squared, being equal to -1. But if you want to just have I as a singleton, a single factor, then it's defined as the square root of -1. And then if you want to perform sum, difference, product, if you need to divide, you're going to need to bust out the complex conjugate, which is just like the same number, only change the sign in between the two parts, the real and the imaginary part, that is. Of course, there's this silly equality of complex numbers thing that gets mentioned, but it's kind of painfully obvious to the most casual observer, I would think. Furthermore, we have, what else could we do here? So there's the product of complex numbers. I tend to do just FOIL myself. I think that's a little bit easier and more familiar. This one's very useful though. If you multiply complex number of the form a plus bi times its conjugate, so a minus bi, then you can go straight to just adding the, summing the squares of their, the real and the coefficient of the complex part. So a little bit of a shortcut that you can take there. Furthermore, if you take the conjugate twice of any complex number, you get the original complex number back. What does this one say? The conjugate of a real number is the real number itself. Yes, of course, because it's kind of like saying a plus 0i. The conjugate of that would be a minus 0i, but 0i is going to be, it is exactly nothing, so it's not anything to worry about. Cool, and then there's some other stuff about here with regard to operations and conjugates. You could just separate them into their own individual conjugates. Cool, cool, cool. And then here, the powers of I, it comes in this little chart. Very handy, something that you're going to want to internalize, or at least for the first 4 powers of I would think would be very useful for you, because as you can see, the pattern repeats, okay? So you don't necessarily have to memorize 8 powers of I, just the first 4 I think would be useful in trying to investigate higher powers of I. Okay, so then there's also this principal square root business that tells you how to extract the I from a square root situation. Okay, so all of that is probably more or less review. So let's just go ahead and bust out several examples just to get ourselves warmed up on the idea of this non-real complex number situation. Okay, so if we wanted to subtract some complex numbers, the way you would do it is you would multiply through this negative sign, right? Which would look like 4 plus 5i, and then it would be plus 8, right, minus 2i. And then you can treat these like terms. You can move them around if you want. If you want to just like underline, the real parts, and then maybe squiggle underline the complex parts, just so that you can combine the like terms correctly, then that's cool. You could choose to just do this in your head too, that's fine. In which your final answer here will be 12 plus 3i. Done. No sweat. With multiplying two complex numbers, Personally, I go for the FOIL. I mean, they do it a slightly different way in their little write-up there, but I would just go firsts would be 5 times 2, which is 10. Oh, and FOIL is this: first, outers, inners, and lasts. The inners would be 6i, and the outers would be minus 5i, and the lasts would be minus 3i squared. Now remember, I squared is -1, so we can have this little bit right here just be a -1. Of course, these can combine, so we could do some cleaning house in order to finalize our answer, because we want to have all of our answers in the form of a plus bi. That's very important for this section, and in general when you're talking about complex numbers that have an imaginary part. So that'll be 10 plus I plus 3 is the simplification of this last term, because it was a -3, but then there was a factor of -1 in the form of the I squared. So then we'll get a final answer of 13 plus I. And that one's done. Great. Now, when you are faced with this ratio, like a division problem with complex numbers, you have to multiply by the complex conjugate of the denominator of the original ratio that you're given for numerator and denominator. So it's kind of like you're coming up with a fun one, all right? A fraction whose value is 1 but has a fun representation. Go ahead and use fun 1 in your daily conversations with random people. And so you can get rid of any kind of imaginary stuff in the denominator, because what you're going to get is, well, you're going to get the sum of squares, or conjugate times its original partner is going to be 1 squared, right? Plus 1 squared, which is the coefficient of the i's there. Now I'm going for this little guy right here. Just want to highlight what I am alluding to, this one, in order to make that happen quickly for the denominator. And then I'm going to FOIL the top, which is at first at least going to give me the firsts are 2, the outers are 2i, the inners are 3i, and the lasts are 3i squared. So that's going to be 2 over, this is going to be a -3, right? So that's going to come into the form of a -1. And then there's 5i otherwise. Now, it's not enough just to leave it in this form, okay, because this is not a plus bi, is it? It looks like an a plus bi all over 2. So what you have to do is what I like to call splitting the numerator, and put each of these like in their own little term with their own divisor of 2. So that'll look like -1/2 plus 5/2 I, where a is -1/2 and b is 5/2. Okay, so that's the format for the final answer that they want for a problem such as that. All right, squaring the binomial rule is going to come in play for part D here. So you're going to square the first thing. You're going to subtract, because that's the operation inside, 2 times the product of the things. And then you're going to add the square of the last thing. Okay, so what does that get you? That gets you 9 here, minus 24i. And then that'll end up being a -1 factor, but you got to square the 4 as well, so it'll be minus 16, or sorry, plus 16. Just a moment. Okay, just checking my notes there. It'll be, because this little piece right here, this little part that I'm circling, is going to be a -1, but then you also have to take this and square the 4 as well. So that'll be 6 minus 16 ultimately. So what's 9 minus 16? That's going to be negative 7. So that'll be negative 7 minus 24i. Okay, great. 2 more examples, and then we will have just a little bit more to cover. I know we've already been talking for over an hour. Just stick with me here, folks. Now, we have several different powers of I going on here, so we could just kind of look at the chart for now. I to the 7th power is equivalent to negative I. I to the 5th power is the same as just an I, so plus I. I to the 3rd power is again a negative I when you simplify it all out. And then, of course, we're going to add the I at the end there. Now here, this negative I and that positive I cancel. This negative I and this positive I cancel, and it's just going to give us a 0 as our final answer for that one. Nice, that worked out beautifully. And then lastly here, we need to remember our rules associated with radicals in order to simplify just the 45 part, but then also recognize that there is a factor of negative 1 in there. So it might behoove us to separate out the perfect square factor of 9 that we see, 5, and negative 1. So just kind of give those their own little space in here. And then recognize that the radical of a product is the product of individual radicals, right? So this right here is I. This right here is a 3. So we can write this as 3 square root 5 I. And that's the order of elements that you want. You want your integers out in front, or rather, yeah, your real numbers out in front. Sorry, not real numbers, your whole or integer numbers out in front, your radicals next, and then your I at the end. That order is best. Okay, almost done here, folks. Yes, we have one last section to cover, but it's real quick. It's basically just using the quadratic formula. Which, if you don't know already, has a fun song associated with it. It could be sung to the tune of Pop Goes the Weasel, I think is how it goes. How would you sing it? So I'm talking about this guy right here. If you were to sing it to Pop Goes the Weasel, it'd go x equals opposite b plus or minus the square root b squared minus 4ac all over 2a. I have another thing that I could talk about. Maybe I'll wait until class to tell you the story that could be associated with the quadratic formula. In any event, the other thing that we want to note from this section is what we can glean about the characteristics of our zeros by virtue of the discriminant. So that is the thing under the radical in the quadratic formula, the b squared minus 4ac. If you just calculate that and determine if it's positive, negative, or equal to 0, you can know the number of real solutions that you have. So if it's positive, the discriminant, that is, and that's what it's called. Sorry, let me write that down. Discriminant. That's what this is called right here. If it's positive, then you have 2 real solutions that are distinct. If it's equal to 0, you have 1 real solution that has multiplicity 2, or they call it a double root in this section, but we know better. It's called multiplicity 2 for that 0. And then if it's negative, then that means you have complex solutions, and they come in a conjugate pair. Okay, cool. Complex solutions that are not real, I guess we should specify. Okay, so what we want to look here for in this example 10, it has 3 parts, is we want to look for the complex zeros, which could be, you know, having no imaginary part. They could be real zeros, or they could be complex zeros that are not real, that have imaginary parts to them. Okay, so with the first example A, this f of x function is painfully simple in order to find the complex zeros, and we don't need to use the quadratic formula because this one is factorable. So factoring it, we're going to get x plus 4, x minus 4. And so the zeros are 4 and negative 4, right? Duh. Like, we knew that. And it just goes to show you that when they say complex zeros, they're just like, what are the zeros? They could have imaginary parts or not. These two complex zeros happen to be real and having no imaginary part to them, okay? Now here, we're not going to be so lucky because this one is not factorable, y'all. So we're going to have to rely on the quadratic formula for this one. But if we wanted to first just do the discriminant, we could determine how many solutions and what type we have, okay? So just because it's not factorable doesn't mean that it's necessarily going to be not real, okay? So let's just look at the b squared, oops, hold on, let me be consistent. So b squared minus 4ac is going to be negative 2 squared minus 4 times 1 times 5, which is going to be what? That's 4 minus 20, which is negative 16. So negative 16 is less than 0, so that means that we have a complex conjugate pair of zeros, okay, not real. And what is it? Well, here's the quadratic formula. I already, have the discriminant part figured out. So I just need to go opposite of b, which is 2, plus or minus the square root of negative 16, all over 2 times a, which is 2. Okay, so simplifying this all the way down, x will therefore be 1 plus or minus 2i. Okay, and they usually have the solution separate, so that means that the zeros are 1 plus 2i and 1 minus 2i. I know, silly, because this double operation is kind of nice because it just, like, you know, puts it all in one bag, but you know, the textbook and, you know, other authors are going to want you to separate it. Now I threw this one in at the end just for fun because it requires that we do a little bit more work, and I just think getting into this problem might be kind of a hoot. Okay, so notice that we are a 6th degree, so not quadratic function that we're dealing with here, but it is quadratic in nature, and we can use a u substitution in order to factor it. So let's let u equal x to the 3rd power, and then we can look at f of x as being, or f of u rather, u squared minus 9u plus 8, and then factor it. Yes, it does factor as a quadratic as u minus 8, u minus 1. Okay, plug back in your x cubes and you have difference of cubes, which is something that we could also factor. So much factoring to do. Okay, so let's do this one first, and that'll be, if I'm not mistaken, x minus 2 times x squared plus 2x plus 4. And this one will be x minus 1 times x squared plus x plus 1. Checks notes. Yes, that looks good. Okay, so there's the factored form of it. So the zeros that arise from, let me underline this in another color, from these two are real and easy to find. So that'll be zeros. So I'll just have a list right here for now. And I'll list the zeros of 1 and 2. And then it looks like I might have some more zeros that may or may not be complex. Okay, so let's go ahead and do quadratic formula on these bad boys. I'll go ahead and say for this one, x equals opposite of b plus or minus the square root of b squared minus 4ac all over 2a, which is just 2. Okay, and so that settles down to, when you simplify that out, x will be negative 1 plus or minus root 3i. Don't worry, I'll write them out separately when I'm done here. And then this one, separate quadratic formula investigation here, this will be -1 plus or minus the square root of square root of 1 squared minus 4 times 1 times 1 all over 2. And so that one, you simplify it down and you'll get x equals -1/2 plus or minus 3 or root 3 over 2i. Whew. Okay, so that gives us all 6 of our zeros. 2 of them were real, and then 4 of them came about in the way of 2 separate complex conjugate pairs. So let me just write them all out. So there's 1, there's 2, there's -1 plus root 3i. There's -1 minus root 3i. Furthermore, there's -1/2 plus root 3 over 2i. And lastly, there is -1/2 plus, or minus. Did I say plus before? I did. So this one needs to be minus root 3 over 2. Okay, thanks for your attention. That is a wrap. Let me know what questions you have in class.